Okay, thank you very much. Thank you, organizers, for giving this great opportunity to talk at this conference. I think I will not be it will not be very far from the truth if I say that the main reason why I am still in science is Ludwig Dmitrievich Faddeev. Okay, so I will talk about about pentagon identities, and to begin with, let me just start from the past. For me, pentagon relation is algebraic realization of 2-3 Pachner move. In 3D triangulations. And so historically, the first example of such a realization was given by Biedenhardt Elliott. In 1953, where they derived the 5-term pentagon identity for the 6J symbols of the angular momentum. But let me just give you start with a combinatorial description of the identities. So let us take combinatorial simplex. So 3. This is not the integer part. This is a set of integers from 0 up to 3.
Dot stands for 2.
For 2, yes. For 2. Okay, so this is 3 simplex. And we can draw it geometrically by drawing a tetrahedron and enumerating the vertices like this. And then, so this will be building blocks of the identity. And then we have to look at the 4 simplex. And yes, those 3. And then we have boundary components, 5 boundary components of 4 simplex minus. So we take out 1 point, and then we end up with ordered 4 tuple of elements, which will correspond to 3 simplex. So these are boundary components. And then in cohomology theory, we know that the parity of I also plays the role of orientation, positive or negative orientation. And so the pentagon identity simply tells us that we collect the odd boundary components in one side and even parities on the right-hand side, and then we equate them in the sense that, so let me put it like this, D3 for gluing equal D4 for D2 for D0 for, and here we have many gluings. And of course, we can just draw it more explicitly like this. And the enumeration goes like this: 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So it's exactly corresponds to this. So gluing, there is just one gluing corresponding to this common face, and here we have 3 gluing corresponding to these vertical faces. And now turning to 6J symbols. How they appear. So we consider the quantum states. We introduce quantum states, which are given just by a map of the edges of 3 simplex to half integers, non-negative half integers, so the spins. And then we have a weight functions, which are given by 6J symbols. So weight functions of they're often drawn like this, so with G101, G02, G03, J23, J13, J12. And geometrically, we just color the edges by half integers, J01, J23, and so on, a 6J symbol. And then, so the Biedenhardt-Elliott identity, so pentagon, so which is a realization of the pentagon, is just a weight function of, so we take a state on the edges of 4 simplex now, and then we use them to produce an identity which tells that the weight function of D1 4 with J product weight function of D3 of 4 J equal same thing as D4 for J D2 of 4 J W D0 of 4 J. But here we take a sum over J13 over all values, which corresponds to this interior edge. So this is a Biedenhardt-Elliott identity, the first historical example of the pentagon identity, in the sense that it algebraically realizes the 2-3 Pachner-Mov. And now let me turn to second part of my talk, which is the present.
But you have to say that the sum is finite or not, yeah?
It is always finite for a given map. There is only finitely many contributions in the sum.
Where is this encoded?
It is encoded in the properties of 6J symbols. So there are some triangular conditions on the coloring. But in general, of course, if you try to construct a TQFT out of this, then when you deal with closed 3 manifolds, you get into trouble of infinite sums. But let me first just say motivation. I'm going to start from this and do something, and the basic motivation for that is a TQFT quantum Chern-Simons with non-compact groups. Okay, so that's a basic motivation. And now the second part of my talk is what's going on nowadays about this activity. So let me start from a generalization. And the generalization is very simple. So we change the set of state variables to measured space. Okay, and then after this generalization, we take, and of course, the sum will be replaced by the integral. By an integral. But now, this step is kind of trivial, but what is non-trivial and makes things work and simplifies drastically is a specialization. And the specialization is what I call a gauge invariance. So what is gauge invariance here? So I take but first there are two things in specialization. So measure space will be replaced by locally compact abelian group. ADX. And the second thing is the gauge invariance. And what is this gauge invariance? So gauge invariance is given by maps from the vertices to our abelian group. And we say that two state variables, if we have a map from edges to our abelian group, and then we say that we make a transformation, a new state variable, which is given by the value of the j plus the values as the endpoints. Okay, so we have an edge and we have endpoints. So our gauge group is given by functions on the vertices, and then we. Sorry? Yes.
Do you take into account orientation?
No orientation. No orientation.
There's no minus sign.
No minus sign, just sum. And then we, so the gauge invariance principle tells that the W of the tetrahedron evaluated at J is equal to W evaluated at JG. And this simplifies the situation drastically. So instead of 6 G symbols, we have a few degrees of freedom. So we had 6 before, but we impose 4. We declare 4 degrees of freedom at 4 vertices spurious. So the true degrees of freedom is just 2. And then the 6J symbol goes to a function of 2 arguments given by where x is given by j01 plus j23 minus j03 minus j12, and y is given by j02 plus j13 minus j03 minus j. Okay, so let me put this way: 1, 2, 0, 2. 013. So we have only two gauge invariant linear combinations of 4 variables. So our weight function will be a function of only of them because of this gauge invariance principle. And then the pentagon relation takes a much more simpler form so that we can write it even explicitly. Pentagon will be psi of xy, psi of uv equal integral psi of u plus y comma v minus z psi of x plus y plus u plus v minus z comma z psi of x plus v y minus z dz. Integration of our group. And this is a simplified version, but I will keep track the fact that we have also these indices. And in principle, we can admit that they will have some extra parameters which distinguish the different indices. So let me restore them. And so this is a beta pentagon. And the subject of my talk is this relation.
I hope for examples.
Yeah. Okay, let us example. Why beta? The answer is following. So psi of xy, example, actually first example. Even historically, I think, is this I x plus y minus iy, where b is a Euler beta function. Okay, Euler beta. Okay, this is I wonder if it is so. In the if you Google it, you can if you're lucky, you can come across 15-term integral identity for for gamma functions. But it's funny thing that you can rewrite it as a 5-term identity for beta function by combining 5 gamma functions into 15 gamma functions into 5.
And just to understand it better, in this case, the group A is what?
Yeah, A is R.
Oh, that's
yeah. And I wonder if probably everybody knows that this is a Veneziana amplitude, and I wonder if there is some significance of this 5-term identity in the string theory context. No idea.
Do you have an example where it's the unit circle?
I will come to this. Okay. Not really, but in principle, yes. Okay, so now now, yes.
This is for field R, right? And gamma is like a local zeta function for Archimedean field. Can you replace R by periodic field?
I don't know.
Then you should get like a local zeta function, and you should construct the ratio like beta.
This should go to the third part, future.
Okay.
Would you take a finite abelian group?
Finitely abelian. No, I don't know. I don't know. I will tell everything I know today. And in my list, there will be no finite abelian groups.
That's a pity.
No, but as you see, my motivation excludes them.
Ja.
And actually, the origin of how this solution is due to myself and Feng Luo and Grigory Vartanov. And the identity was proved by using Spiridonov's famous elliptic beta identity. Spiridonov beta, elliptic beta.
Even in the classical case of standard gamma, you need elliptic.
Today I will give a independent proof, but originally it was proved as a reduction of Spiridonov's. Okay, now let me turn to Fadeev type functions.
What about Chern-Simons? There was Chern-Simons. So far we haven't seen Chern-Simons.
No, it's motivation. My talk is not about Chern-Simons. Fadeev type functions. So what is it? So it is a collection of 5 functions on real line. Which satisfies this identity. Phi 1 of P, phi 3 of Q equal phi 4 of Q, F2 P plus Q, F0 of P. With Heisenberg operators. PQ, which satisfy a normalized commutation relation. And examples, there are actually few. Of course, the first example is a quantum dialogue. And a few versions of them. But second example is kind of trivial. Yeah, so let me do the fj of x is phi sub h bar of x. But this is a concrete function. I don't have time to write, but Leon talked about it already in the first lecture. But the second is a kind of trivial, just unit function. But there is also some less trivial relations which are given by ai e bi x squared by Gaussian exponentials, with the real part of bi is negative. So at least, as you see, there are 3 examples of Fadeev type functions. And then, now let me state the first result. One. Okay, so let fj of x and gj of x, 2 Fadeev type functions. Then psi of xy given by fj E 2 pi I p hat x plus q hat y j solves beta pentagon with a equal r. So here is an example. So you can take any pair from this list and plug it into here, and you get a solution. And in the so the particular cases, for example, 1 plus 1, which means that fj of x equal gj of x equal phi of h bar of x.
Это такие Вигнеровы функции, да, вроде бы называются.
Не знаю. So we take this, then psi of xy is a single integral phi h bar of t plus x half phi h bar of t minus x half e 2 pi I t y dt. And again, this generalizes beta function example by introducing an additional deformation parameter h bar. So if you wish, it's a quantum version of the beta function example. And it also comes as a reduction of Spiridonov's beta.
Есть бета-интеграл, что вот эта вещь равна произведению трех. Это, ну, вы же знаете.
Да.
Это другой.
Даже, ну, для того же.
Can you explain what do you mean by this scalar product fj?
Yeah. So just think of f's as elements in the Hilbert space,
Okay.
and then you just sandwich it. In the quantum mechanical sense.
Can you hint at the proof?
I say,
Sorry?
Can you hint at the proof? Because
Hint, direct calculation. Just write it out, substitute, and get it. No, unfortunately, I don't have time, but of course,
You have 10 minutes.
yeah, I have third part.
For the identity, it readily implies this one.
Yeah. And now let me give so this is A, B. We can take 1 plus 2, right? We can sandwich between unit and the Faddeev function. Then psi of, which means that fj of x is 1, and gj of x is phi.
So the psi of xy is what is sometimes called the Weil representation of the operator fg.
Okay. Yeah, it would be nice to see if there is some history around this kind of.
So if you take any two wave functions like that, I think, as Andreev just said, that it's called the Wigner distribution in quantum mechanics.
I see. But here we impose. Okay, then psi of xy is e minus pi I xy Fourier transform of Faddeev of y. So you see in this case the dependence on the first variable very explicit. And just a side remark. just a side remark, is that it has automorphic property with respect to the first argument. Psi of x plus lambda y is e minus pi I lambda y psi of xy. Okay, and then here comes the third part. Let me call it future. And I just put it as a theorem to let psi j of xy be a solution of beta pentagon satisfying the condition so psi of psi j of x plus b y is equal h of b of y psi j of xy, where b is in a subgroup and h is a group homomorphism from B to Pontryagin dual of A. Group homomorphism. Such that h of B evaluated at B prime times h of B prime evaluated at B is equal 1. Okay, this is the hypothesis of the theorem. Then psi tilde of j of xy given by integral over b psi j of x y plus b hb of x plus b db. So b is a subgroup of a locally compact group, so it has its own Haar measure and so on. So I just take this integral.
In the case of when A is R, what is B?
B is typically Z, so it's a sum. Then psi tilde solves is automorphic. In the sense that psi tilde j of x plus b y equal h of b of y, as in the hypothesis, but it is automorphic also with respect to the second argument, h of minus b x plus b psi j tilde of xy y, and solves the beta pentagon over the quotient group.
Rina, H is defined on B, but X plus B is not necessarily to be in B.
No. H comes to Pontryagin dual of A, so it can be calculated on any element of A. But B also as a subgroup sits, so it makes sense.
No, but H, so I'm confused. This is H of B, it's evaluation H on B first.
So this is a character.
No, I mean the first definition. You multiply psi j by h.
Yes, so H is H of B is a character on A.
Oh, so it's B's index.
Yes, yes. So the first argument of H should be always be in B.
There is no first argument in h in the upper.
Sorry, H of B. H of B. Sorry.
Okay.
Yeah, that's.
Now it's fine.
Yeah. Okay, so that's an example, and then you can see that if we look at this example, it has exactly automorphic properties if you take lambda equal to 1. If lambda equal to 1, then all the hypotheses of the second theorem are satisfied. And in this way, we get automorphic beta pentagon, which is not a function on the circle. So it will be B will be Z, A will be R, but it will not be just a function on the circle. It will be a line bundle section over two torus. So in this sense, the answer to your question is affirmative. Okay, thank you very much.
Can you use this like in the zero to Kashaev approach?
Yes, yes, yes.
And what are they?
There are some invariants which asymptotically give hyperbolic volume. So the TQ of T is constructed by now already. So it's my joint work.
And why it gives the volume?
It's a quantum dilogarithm somehow generalizes classical dilogarithm, which enters the volume calculations in classical hyperbolic geometry. And this is the intuitive reason why if we cook up a quantum theory from quantum dialog, then it should give in classical limit the hyperbolic geometry. And it happens to be so by explicit, on the level of explicit examples.
I just wonder if you just take the old paper Andrea Vela, which treats commutative relations for any locally compact abelian group, and then you can repeat everything in the
Yeah, good point. One should do so. Thank you.
Well, I have two questions. So first, you mentioned that this eta pentagon comes from Spiridonov's integral.
Yeah.
So on the elliptic level, is there a little counterpart of that, or?
No idea. Not so far. At least not known.
Second
Open question.
Do you know representation theoretic interpretation?
Open question.
Okay.
Future.
Something about the relation to Chern-Simons.
Well, Chern-Simons, the only justification for Chern-Simons is a quasi-classical limit. We get hyperbolic volume. But Chern-Simons is not defined anyway with non-compact group. So there are no other means to compare with.
Other questions? I have one. The exponent of this one has meaning in instanton calculations. It has correction.
Logarithm, you mean? Logarithm.
Log.
Yeah.
Sorry. So if you now add the instanton part, this is perturbative part. Did you check that this?
No, I think this is instanton part.
No. There are second parameters. There is a Q, there is H bar, and there is another parameter Q which counts instanton. This is perturbative. Well,
I say that this is instanton part. I can argue this.
so where is the second parameter? Where is the second parameter?
There's no Q in this business.
Right. So what I'm saying is that I want to add to it the infinite series in Q.
Yeah, but because this story is topological, and now the Q would be parameter for complex structures. And that's
Yeah, might be.
So do you know if it satisfies anything similar? If I add,
Probably not.
there will be some other equation, similar equation. Well, there is one. First of all, Nakajima had derived the equation very similar to this for instanton.
Right, I'm confused. I mean, in the usual quantum Kashaev approach, you take the quantum 6J.
Yes.
And you have the Q, which is a deformation parameter. I mean, you can
Yeah.
vary discretely. Do you have something like a Q also in this context?
Yeah. You have H bar, and H bar is
But that's a fixed number.
yes, it's a fixed positive number. So h bar is 1 over b plus b inverse squared, and q is e 2 pi I b squared. That's a connection.
So you could look at the results, so the volume, you get a whole series of volumes for it.
Yeah, when h bar goes to 0, yeah.
Oh, you have to take h bar going to
Yeah, yeah, of course.
What happens if you take h bar going to infinity?
I don't know. Future.
It should be covered by self-duality, no? It is,
No, but by self-duality, b to infinity and b to 0 is equivalent to h to 0, but not to infinity.
Okay, so no other questions. Thanks, Renat.
Thank you.